Hello guys, thank you for coming to OLED Wave channel. We read the latest archived works, including the classical papers on speech and NLP. Today, we're going to be continue reviewing the paper Language Models Are Few-Shot Learners. It's actually the classical GPT-3 paper, and the GPT stands for generative pre-trained transformer. We have finished the abstract introduction and the approach sections last time. So this time, we're going to be starting from the results section. Okay. In the results section, the authors, they discuss the performance of the GPT-3 on different tasks. First of all, they have demonstrate in the figure 3.1 that the loss can be reduced if you increase the size of parameter, or how to say that the ending validation loss can be further reduced by increase the size of the trained model. If you see this is the largest size of the model, okay? The yellow line. And you can see the loss here, the ending loss, validation loss, is way smaller than the loss that achieved with a smaller, what do you say that? Smaller model. And definitely the computational cost is increasing when the model size went up, and it follows the power scaling law. I think there's a famous paper. It's called Scaling Law of the Language Models. You can check my channel, and you may be able to find that paper reading. Scaling law, something like this. I think it's of language model. Okay, but I think now I wanna go to the 3.1 section. It's language modeling. First of all, the authors they test their trained models, or the largest size of their trained model, on the pantry bank task, or on the validation set on the pantry bank. And the sorta state of art algorithm, it's also zero shot. They can only achieve 35.8 in terms of language model perplexity. But the proposed GPT-3 can vastly reduce that perplexity value. You may ask, you see, these guys, they talk about the loss at the beginning, then they talk about the language model perplexity. Are they related? Perplexity. Sometimes I use PPL, language model perplexity. Are they correlated or related? I mean, indeed, they are the same thing. I think because I'm a speech guy, I worked with language models, so I think if you guys are with me, I can give you some deduction on why I think the validation loss or cross entropy is equivalent or necessarily equivalent to the language model perplexity. Okay, I want to change the color of this red. First, what is language model perplexity? Sorry. Move this. Clicker. Okay. Well, the definition of the language model perplexity was given a trained language model. Let's call the model P. Okay. Given any word sequence or word, the probability of the model. Okay, this is the definition of one language model. Say this is a word sequence. Okay, this is like a word 1 to word n. This is the probability of this. I have to click it. That's the definition of a language model. And you may say, suppose this is test set, and the language model perplexity, this definition is, this is the, how to say that, normalized. Not doing well. Is equivalent to normalized inverse probability of the word probability on the test set. Remember, this is on test set or validation set. You may ask yourself why it should be on the test set, not on the training set. Because on the training set, that doesn't make sense. On the training set, you have seen all the words, and so to remember, you use the conditional probability to compute this probability. For instance, this can be written as W1 times W2 given W1 to get Wn given all the word history, right? On the training set, you have seen all the cases, right? All the what do you call that? The combination of these words. So this probability of this word would always be 1, right? So you won't get a different language model perplexity if you change the training set, right? But on the test set or validation set, there is always some cases that's unseen. What do I mean by unseen? I think for the computer vision people, they call that distribution shift. But for the NLP, it's more easy to understand because suppose in the training set, it's all talking about the food, different types of food, right? But suddenly on the validation set, you shift the topic to soccer. Yeah, definitely. Then the problem would be what's the probability of Leon Messi? Right? Then you have never seen this word combination in the training set before. So this is really hard to estimate this. And usually, if you have not seen this in the training set, it would be using some smoothing technique to get this probability. And then remember in the smoothing technique, for the unseen words combinations, the probability is usually very, very small. and this is very close to zero. Close to zero. And what if your the probability of the word sequence is close to zero? Look at the equation here. That means your language model perplexity would be very, very large. I think 10 years ago, I think I saw some language model perplexity that's over 200. That's a very, very, how do you say that? It doesn't mean that it does not necessarily mean that the testing or validation set has a distribution shift. It also could be because the training set is very, very large. It covers a lot of things, but they cover too many topics. And then the test set might not be a good match to the training set. Right? Okay. So you can see that if you want to estimate the unseen word sequence probability well, you might want to reduce the language model perplexity as much as possible. So you want, I usually call this LMPPL. That's my preference. Okay. Then you want the PPL to be as small as possible after your training, okay, on the validation set. That's your goal. Remember this. But let's look at what the cross entropy is, okay? Suppose you have a true distribution. Let's call that I hate that I used the P already. Anyways, this does not necessarily to be word. I just want to say you have a random variable x, and then you have let's say it's a discretized probability p of x. This is x. You have certain type of distribution, okay? And then you could have estimated distribution of p of x. This is your estimated version. Okay. Let's call that q of x, okay? First of all, what is the entropy of the random variable x? Let's say h of x. What's that? This is my question. So the entropy denotes the information or the number of bits that is being stored in this random variable. That means the random variable has a certain type of distribution, and that distribution, when the distribution is settled, that means the random variable carries certain amount of bits or information. And I think most of you have definitely seen, remember this graph, right? This is the probability, and then this is the h. Probably have seen this. That means suppose your random variable can only take 0 or 1. The probability of x equals to 0 and 0 equals to 1, but you can see that if they are evenly distributed between 0 and 1, you will get the maximized entropy. That means, or say, entropy means, how do you say that? Either the information stored in that random variable, or sometimes people call that uncertainty. In the random variable. And I think it's easy to write the entropy equation. Okay, right? The entropy equation it's you have to have the minus sign, otherwise this won't be positive. Okay, does it make sense? This is the entropy equation. But what is the cross entropy equation? Let's say called H. I think I still need to use hx, but here sometimes people use the hp and q to refer to this as a cross entropy. That means you have a estimated how to say that? I think it's better to write in this way. Let me use x and y. So x distribution is p of x. Although you have an estimate of the x distribution, that's called as a estimation. As I think kind of a confuser here, but I think you can use suppose you have I mean let's say in this way. Well, suppose you have an estimate of the p of x and you got q of x, okay? Then for distribution, you can regard this distribution as another random variables distribution. That's called a y. So you can write down the cross entropy of x and y, or between x and y. Well, this is written as also the minus sign p of x log. This time is a q of x. Okay. And you can see that this thing is always, I think, would be larger than h of x because of the Jensen, not Jason, Jensen's inequality. Check this. I won't explain it here. And then you can see that whenever you try to make your qx to be as close as to the p of x, then you can see that this value would be approaching the entropy of the original random variable. And in this way, you cannot make it exactly the h of x, right? And as we all know, this is always larger than h of x. And then if you remove the negative sign, sorry, it's smaller. I'm not, and my mind is not rolling very much because the JSS equality, this is always smaller than h of x. And then this is why even you have a very, sometimes you have a very good estimate of q by x, you're still not approaching, you're approaching the h of x, but you're not getting there. So this is why lots of people are saying this is a cross entropy, right? Cross entropy. And then indeed you are think it's really too cold here. This is always greater or equal than h of x. I was correct at first, I think. And then your goal was to minimize this. So this is why in the deep learning or in the machine learning, you see a lot of people they're saying they're trying to minimize the loss, or they actually minimize the cross entropy, right? That's the goal. But you ask, okay, I understand what is cross entropy. I understand what this is perplexity, but why these two things are connected? Let me show you. The reason it's connected was because if you I think this is the tricky part. My mind is not rolling very much today, but I will try to see if I can get it. Let's say you want to minimize the PPL, right? That was the goal, right? Let's say you want to minimize the log of the PPL. That is the log 1 over n. Sorry. Not like the raw PDF. Is correct. This can be written as n log. This is a minus sign. Got a minus sign. If w1 to wn. We're getting there, right? So let me write this here. No. This again. Log PPL equals to and then if you're using the IID assumption, then you can write this as log PWI given history. Make sense? This is I's history. Then what's next? And this summation can be moved to here. Are you with me? And let me write down the entropy equation right here, okay? And this time, let me change the h of x to be word, okay? I no longer use the x, I use the h of w. Okay, so I think this time I would get P of WI given history times log cross entropy. Okay. Better not to write this one. Better to write. I think that this is called cross entropy. Is actually h of x minus hx minus xx and y. I think. I don't think so. But actually this is the estimated. How do you say that? Did I use a Q? Let me use estimated. Okay. And suppose my words are having the uniformly distributed. Okay. Then I can write this. Yeah, I forgot the minus sign. And I can write this as, because this is I from 1 to n, right? And suppose this is evenly distributed. This equals to 1 over n. This equals to minus 1. I equals to 1 to n log wi is history, right? But actually, this also should be p prime because this is all estimated probability of the model, right? This is your language model's probability. That makes sense. This is also language model's estimated probability. Then you can see the two things are the same. Did you get it? So you can see log probability equals to CE, or say language model probability is actually equivalent to 2 over CE cross entropy. Usually the cross entropy is positive, right? Then PPL is also positive. So you can see I connected the PPL perplexity with the cross entropy. So they are the same thing. I hope you get it. Let's go back to here. And this is why I think the PTB for the zero shot case, the PPL dropped so much that actually meant the GPT-3 had a very significant validation loss drop compared to the sort based method. That makes sense to you? And I think this is my personal opinion. Because this is a significant drop or vast drop in PPL, that indicate the success of the zero shot GPT-3 in the following tasks. 3.1.2 lambda. I think there's something weird here, but I think the author didn't get it very straight. Here you can see that zero shot is better than one shot, but I think the author's explanation was zero shot use a different format from one shot and few shot as described in the text. Never seen that in other experiment. I think since I'm now an OP guy, I work on speech, this doesn't bother me much. But I think it is a interesting thing that needs to be checked, because you can see that when they yeah, also the PPL also is also strange, right? You can see zero shot PPL is actually lower than one shot PPL, but for the other ones that are fine. See, this is okay. This one is strange again. I think it related to the task. Okay. Yeah, I forgot to mention the lambda is trying to guess the last word in a sentence. Open domain QA. This is another task, 3.12, I think. You can see that for the natural QS and especially web QS, the zero-shot GPT-3 got very worse result. That means web QS and natural QS has a very significant distribution shift compared to the training set they use. But interestingly, after a few shot in the few shot learning scenario, actually after that, especially for the web QS, the GPT-3 is not so bad compared to the fine-tuned SOTA system. And for the trivia QA, they actually got better. This is nice. Hella swag. I think I will skip that. Closed book QA. It checked the ability to answer question about the broad factual knowledge, like a fact check. Yeah, this one. This is a trivia QA. It got better. You see this? The model when the model size is the largest, they can do better than fine-tuned SOTA in the few shot learning scenario when the number of shots is 64. Close the book QA. Is there a table? Table 3.3. Wait. Table 3.3. Here. No. Table. I mentioned that. Open domain QA. Wait a second. Open domain QA and just got confused. Oh, I see. They are actually the same thing. Am I right? But they changed the name. How about that? Translation. I think translation is intriguing to a lot of people, including me. For those of you who are interested in the translation but haven't checked the translation before, you should first check the metric, which is the BLUE score. I forgot what BLUE stands for, but just search the BLUE keyword and you know what it meant. Because it's not like ASR, the answer is certain, right? But you can either translate in this way or in a paraphrase the way. That's both fine. But because in a paraphrase way, you would still have some word overlapping with the original answer, so they will still count you to be correct in the BLUE score metric scenario. It allows you to paraphrase the answer. They mentioned that they use the Common Crawl database. So this is a database with about 83% of the text to be English and the rest to be other languages. Let me quickly check what it have. Why can't I click it? Anyways, if you look at the result, I don't think it's getting. I think it's going probably going in the right direction, but it's not there yet. Especially when going from English to other languages, for example, English to French. See, even after a few shots, this is a big difference compared to SOTA. This, you can see, big difference. Romania, big difference. And it seems that to me, for these scenarios, few shot does not help much compared to zero shot. Not this one. And then, but when translate the other language to English, they have shown that, okay, this is better. Interesting. This is better. And this is almost as good as Romania to English. Roman or Romania? Okay. What does that mean? I think the reason was because the most of the text in that training set is English. This is probably explains why this thing can do well when given a non-English prompt and can generate English text fairly well. You may ask, why didn't it work so well when they're going from English to other languages? My understanding is that to get the to generate other languages, you have to have a good understanding, or you say have seen enough amount of text of that language. But indeed, especially you see for example, Roman or German language or French language, they have not seen enough amount of it. This means you can think about this. The GPT or the output layers softmax, and I think the probability, again, we come to the language model perplexity stuff. You would see that if there is a test set of French, you would see that perplexity value on that test set is fairly high. That means the entropy is large in that French random variable, and that also means the uncertainty in translating English to French is very high. But the other way around, other languages to English, you can imagine that the English regarding the English, the language model perplexity might be small, very small, and that means there's no much uncertainty when doing the translation task, so they can do better task, and they can even do better task than job than the SORA system when given a few shots. This is pretty impressive. You see the numbers, because if you check the SORA system, they are fairly supervised. They have lots of training samples. Okay. I think I would just jump over some of the result for the winner grade. I think it's winner grande prize. Determine which word a pronoun refers to. Okay. I think this something has some logics or deduction. So my hunch was whenever it went to some sort of thing that needs to be, deduction or reasoning, the chat GPT or GPT-3 didn't do well. You see the fine-tune sorta is here, and the few shot learning didn't even supersede the fine-tuned robota. And I think our human beings are fairly good at reasoning compared to the machine. There's a big gap here around. Winograd, common sense reasoning. Yeah, same thing. Which Pika test server. Yeah, I think you see, common sense reasoning. Interesting. It's not deducting, right? It's not reading comprehension. It's a common sense. Common sense wise, if you check, Pika is fairly good. See, better than Sorta. But the other ways are not so good. Easy, even didn't do well on the easiest case. OpenBook POA not doing very well. So I wonder why. Oh, yeah, I think this is still reasoning. Yeah, reasoning is the weak part of the generative model or GPT model. I think the reason it did well might because, as the author mentioned, the potential contamination issue on the Pika test set. Yeah, you see, this is the corresponding to here. It's better than the fine-tuned Sora. And also reading comprehension, I don't think he can do well. Yeah, you see that? It's still 45% behind the Sorta in terms of reading comprehension. Superglue. Superglue is, I think, is that some type of intention and a slot filling task? I think I'm right. It's a natural language understanding task. Yeah, you see, again, it comes to the understanding part. It's not doing very well. You can see that on the QA is behind the fine-tuned Sorta. Yeah, this is the breakdown or the details of the superglue task. It's way behind. See this? Way behind. This is see, this is way behind. And also they demonstrate if I can change the size of the parameter, say this is the largest model, they say they can do better than the fine-tuned BERT, but not as good as the fine-tuned Sorta. And interestingly, fine-tuned Sorta is very close to human being performance. And they also played with different size of the for the few shot learning. They also changed the size of the shots. They say if you give me 32 shots, I can do better than fine-tuned BERT, but it's still not as good as the fine-tuned Sorta. Okay, NLI, I think natural language inference. Yeah, it's not doing very well. You see, it's even behind the fine-tuned BERT. Not doing very well. Okay, I think I'm gonna stop here because section 3.9 is a long section. So what did you get? If you like my explanation, please subscribe our channel, and we will continue the section 3.9 and the section 4 discussion in the next week.